Welcome to the 16th lecture of the course on basic building blocks of microwave engineering. Now, in previous 3 modules, we have seen first the characterization or model for the microwave transmission. Then in the second module, we have seen various transmission structures which can carry microwave signal. In the third module, we have seen various passive microwave devices used for playing with microwave power, divide, combine, etc. And in this final module, we will see some active microwave devices which are used for various operations in microwave circuit. In this particular lecture, we will see the active devices used for detection and switching. Now, advantages of microwave solid state devices, that they are small size, they are of lightweight, any solid state device, they have high reliability, they have low cost and amenable to microwave integrated circuits. That is why solid state devices are heavily used in microwaves. Now, first we start with diode, the simplest solid state device. Now, mainly used in all low power applications in microwave, like for detection, then mixing, that means changing the frequency of the signal, then frequency multiplication, phase shifting, attenuating, switching, limiting the amplitude, amplification, oscillation. So, diode can do all that. Now, in this lecture, the diodes that we will be discussing, we have chosen few applications which are important. First, for detection and mixing, generally crystal diodes are used. So, we will see crystal diodes, though there are other diodes like Schottky barrier diodes, etc. Then, for switching operation, actually this switching is also called modulation, that for on off switching, then attenuation, modulation, phase shifting, limiting, PIN diodes are used. So, we will see PIN diodes in microwave. In a typical microwave bench, these PIN diodes are used for on off modulation of RF signal by a 1 kilohertz signal, because the detector is crystal diode that cannot detect the high frequency signal, but the on off modulation of 1 kilohertz that it can detect, and the VSWR meter is also a tuned amplifier tuned at 1 kilohertz. So, PIN diode does that modulation, actually it is on off switching. So, that will be discussed. Then we will see oscillation. So, for oscillation, solid state diodes are GaN diodes. So, we will see that. Also, we can have use impact diode for oscillation, and also for amplification this impact diode can be used. So, we will see these 4 diodes in this lecture. Out of that, the GaN diode and impact diode will be discussed in a subsequent lecture, but in these diode basically we will be seeing the first 2 diodes, detection or detecting diode and switching diode, mainly crystal diode and PIN diodes. So, this is a picture of a crystal diode, very simple structure. Now, you see this is familiar, that in this is the slotted line, the waveguide, there is a slot cut there, and this is the mount. In this the detector fits, so that detector can detect. We have discussed in case of rectangular waveguide T10 mode, that in the middle we cut a slot. So, there is a slot cut, and in that slot this carriage, when it moves, basically the detector is moving and it can sense the electric field. Electric field is also highest at the minimum. So, it has a good sensitivity to detect that. Now, this is a typical microwave bench. Here you see that this is the detector diode is here, inside this mount is a coaxial mount, and from that sorry, I am not doing this is the detector diode here, and through this detector diode the signal is taken to the no that is different. So, this is the detector diode, and through this it is taken to the VSWR meter for finally displaying, correct. So, detector, this is the you have a tunable probe. Now, inside that you see this detector is there, and when the detector is sensing, it is basically sensing the field here in the slot, there it is sensing that field that is taken, and then it is taken to either an ammeter or a VSWR meter. So, it has an RF bypass choke and 1 kilohertz signal is passed there. So, RF signal is bypassed here, whatever RF signal is still present after detection, that is choked here, and so this is the detector diode. You can see this is the tunable probe. Now, what is this detector? This is basically a crystal detector. There is a pointed tungsten wire. So, this is also called sometimes point contact diode. Diameter is roughly 0.8 millimeter dia. Now, this is a silicon chip. The tungsten make a contact with that silicon chip, and that acts as diode, metal and silicon. So, just like Schottky barrier, you have this semiconductor and metal, their contact. So, you get a diode there. Now, in the diode circuit, already with the diode there are leads etcetera, as you can see in metallic electrodes etcetera. So, in high frequency you know that they give rise to some inductance and resistance. So, the leads etcetera of the diode, they give this Ls and Rs, but basically this is the diode. The diode, any semiconductor junction. So, you have a resistance there in the junction, also you have the capacitance, because there is in the junction there is a gap created. So, that is why Rj and Cj, and Rj is small for forward bias, that is the diode, and large for reverse bias. Now, this Ls also there is a, throughout the thing there is a coupling capacitor. So, Ls and Cc can be tuned out by matching elements. So, what remains in the circuit is basically this resistance, lead resistance, and this RC circuit, parallel RC circuit of the junction. Now, diode detector, this up to 10 watt of power it can handle, it can detect. So, its IV characteristic is the well known IV characteristic of a diode, and you know that at very in the forward bias region, just when the signal is small, you have this is I is proportional to V square, this is the square law region. After that, when the signal is further increased, this becomes almost approximately the linear region. So, that is why below this 10 watt up to this you can use the diode. Now, this is the famous diode equation, all knows that I is equal to I naught reverse saturation current e to the power alpha V minus 1. This alpha, all of us know that it is 1 by n Vt. Vt is the thermal equivalent voltage, that is 26 millivolt at 17 degree room temperature, and n is a parameter, it depends on the diode. Now, for crystal diode it is approximately 10, for Schottky barrier diodes it is 1.2, 2 to 4 roughly is for various diodes, but for crystal diode it is 2, but still it is not always 2. So, since it is a precisely if you want to measure the signal, we have an experiment in our lab, that calibration of these. So, basically what we do with the diode, we put it into the vary the various voltages and note the currents in an ammeter and plot this graph, and from the slope of the graph we find out what is the value of n. Now, typically in our labs we get 2.2, 2.3 in that range, but obviously it is voltage dependent. So, of the voltage of a particular source you can always calibrate the diode, that gives accuracy to the detection thing. Now, this is what I was showing. Now, this is the coaxial probe is there. So, there is a probe, the inner conductor, with that the diode is connected, and then you have this signal taken. Now, there is this diode, then detected output. As in that circuit I explained, the bypassing capacitance is there for putting the RF, etc. And also there is a shorting plunger. So, by this you can just move the penetration depth of the diode, because sometimes you do not get good signal, that time you penetrate it further. So, that you can send some signal, but it is always advisable to very loosely penetrate it, because if you penetrate much, this coaxial probe, that field will disturb the actual diode field. But if you do not get signal, that means signal is weak, that time you need to penetrate it further. Now, for small AC signal, we know that we have I is equal to I naught this, but there are also higher order terms, because diode is basically that portion is a nonlinear thing. So, you can, if your signal is V cos omega t, you can put it into this series. This is actually taking some higher order terms, and from there I can see that the DC signal that the diode senses, that is proportional to V square. So, diode DC current is square of microwave input power. V square means microwave power. So, the diode detection DC current, that is square of microwave input power, hence the name. This is also called square law detector. So, the AC components are filtered out by detector circuit, that we have already seen, that these higher frequencies harmonics, this cos omega frequency, 2 omega frequency, they are filtered out by detector circuit. Now, for large input power greater than 10 watt, the VI characteristic, as we have already seen, that they become more linear. So, the square law does not hold there. So, that is why if you want to use it in that case, please attenuate the signal. So, that typically it is below 10 watt, or from your whatever purchased detector diode, you see the IV characteristic roughly where it is up to which it is square, you restrict your input power to that. And obviously, in the reverse biased output case, that means when the when you have a reverse biasing in the on off modulation, that time it does not detector gives any power current. So, nearby 0. Now, as we said that we can tune out externally that LS and CC, but this circuit remains. So, this is the diode detector circuit. So, let us assume that the voltage across the diode sensed, that is V, and diode has created a current I. So, total power that has come to the detector circuit, we can easily find Pt total power is I square R s plus this V square by R j, okay. And useful power absorbed by the diode junction, we can write that P A is power absorbed, that is V square by R j. So, power loss is useful power absorbed by total power input. So, P A by P t, and that expression if we do, it is like this. Now, I by V we can put there the admittance in the junction Y j. So, if we do that, and that Y j is nothing but it is the parallel combination of R j and C j. So, we can put that value, and then finally, it becomes, you see, a function. So, lead resistance R s, that affects the power that you can finally get. So, that is why you should try to make the lead resistance, you see our idea is to make this ratio as high as possible. So, that our detection sensitivity increases. So, you should make R s small, so that we get this ratio high. So, lead resistance should be as small as possible, and also diode junction capacitance, that should be made small. so that this ratio becomes high. Now, microwave detector diodes are quite sensitive and you need not bias it, because whatever it is normally in the square law region. So, no extra biasing is needed and they are quite sensitive, give you good amount of current you can get, detection sensitivity is good, because lead resistance etcetera they are made to minimum, capacitance made to minimum, obviously due to the metal contact. The diode is mounted on a coaxial line containing matching elements, so that VSWR is kept at less than 1.3. You know, VSWR 1.3 means very low reflection coefficient because of this matching. So, it is almost good. Today, we have seen that 2, 3 etcetera VSWR is not good. If VSWR is less than 1.5, that is a good well matched circuit we say. So, very few power lost in reflection. A RF bypass capacitor in the output circuit prevents coupling of signal to VSWR meter. So, VSWR meter output impedance you can select it either as high or low, and detector is matched using a short circuit stub. That plunger that we are showing this probe. So, this when it makes this thing, the stub that also balances. So, it makes you the penetration depth also by the stub, there is also a stub there, by that stub you can always match the short circuit stub. Now, the next diode that we see is PIN diode. Do not write P small I small n, these are all capital. P is the P type semiconductor, I is intrinsic, there is an intrinsic layer, non-doped layer, and then there is an N type semiconductor. So, this is an PIN diode. PIN diode equivalent circuit, as I said PN, but actually they are heavily doped. So, they are called P plus and N plus. For every material there is a limit before, if the doping is more than that we call it P plus and N plus, and there is a intrinsic semiconductor, intrinsic layer of width W. So, this intrinsic semiconductor, this is a highly resistive intrinsic layer because no doping is there. So, electrically variable resistor related to the I layer thickness. That means, this poses a basically acts as an resistance. So, if you make it is more thick depending on the resistance, you can change that. Now, again the same thing you see, the diode will be represented by this C j and R j, then there is a lead resistance and inductance, and also throughout there is a, because there is a total gap there. So, there is a C p there. Designed such that under 0 or reverse bias R j is extremely large. So, when the either 0 bias or reverse bias R j is large, that is any diode, and C j that becomes dominant, its value is typically 0.02 to 2 picofarad, C p L p R s negligibly small. So, basically the diode gives you this R j is quite high under reverse bias. So, you get a high capacitive impedance. Similarly, under forward bias, that is when the frequency is less than this. So, R j that is quite small, and R f is typically forward resistance, that is 0.1 to 2 ohm, and from the circuit you can easily see that it is R j plus R s, very small resistance. So, that means basically this diode is under reverse bias, it gives you a high capacitive impedance. So, it is as if open, and when it is forward bias, then it is a very small resistance. So, almost a short. So, switching action by changing the bias. So, it has two states. So, either you have a open circuit or a short circuit in the switching. In the forward bias short circuit, in the reverse bias you get a open circuit. And there are various ways of mounting. The popular ones are the shunt mount. So, pin diode is, this is the line, RF transmission line. So, RF is coming. Now, you put the pin here. You can also put the pin in the series direction, but then the other circuit elements will be different. This is a good choice in our laboratories, etc. We make it pin diodes like this. Now, also there is a inductor here and capacitors here. So, AC blocking inductor, generally it is realized from a high impedance strip line section. Yesterday we have seen strip line section. So, that inductor is fabricated from that. Fabricating inductor is a good engineering thing. It is quite difficult to do at various as a lumped element to fabricate inductance size, etc. becomes prohibitive, but if you use transmission lines like strip lines, etc., you can get a good inductance. So, also that is very planar circuit. So, easily you can put it there. So, this is for putting the DC bias, so that it blocks the ACs, this inductance, and you get the DC there. Similarly, DC blocking capacitor, you put the capacitors which do not allow the DC to go into the transmission line. This is basically realized by putting a gap in the line. So, in the transmission line you put a gap, that gives you fabricate this DC blocking capacitor. Now, as I said, when I reverse bias, this is basically it is an open circuit, high impedance across shunt. So, RF, if we know, if RF signal sees an open circuit, then it can transmission goes, because the whole signal it sees a high impedance path. So, it goes on seeing a thing, and RF signal goes out, just like an open circuit. Forward biasing, when the thing is forward biased, pin diode is short. In a short, the full reflection takes place. So, transmission, there is nothing that goes here, hold the RF energy that gets reflected from here. So, that means, now please remember that when in the other case, when high impedance is there, so at this point the what will be the total voltage wave, because reflection coefficient of open is +1. So, that time the total voltage that becomes twice of the maximum voltage. So, the whole circuitry in the path, they should be able to withstand that twice voltage there, because if you put a open like this, so the all these places they will get a voltage that is twice of the thing. So, transmission is off in the forward biasing case. This is quite easy to understand. Now, obviously, in practical cases, we do not, forward bias does not mean that purely it is a short circuit. So, some non-zero resistance is there, that is why we can say that isolation between input and output is not infinite, but still it is a good isolation that provides. Similarly, due to non-infinite impedance, because ideally at reverse bias you should have infinite impedance, but that is not true. So, non-zero insertion, some loss is there in the thing. Now, this is a, you see this is the pin diode modulator. So, there is a Gunn oscillator, we will see Gunn diode later. So, based on that there is a Gunn diode oscillator, a Gunn oscillator, and then we put a isolator here, because this, as I said, that there is, in the case of reflection, when the pin diode is there, then the full signal that comes back, and in terms of reflection, that voltage will come twice the voltage. Now, that voltage, if it is comes to the Gunn diode, it may destroy the Gunn diode. That is why always you know that the diode, any oscillator circuit or any source that has a very small resistance. So, if a high voltage comes there, there will be large current, it will flow through the source, and source may get destroyed, because its resistance is very small. So, that is why. So, that is why we put an isolator, so that the reflected power from here that cannot come to the source, but while going it goes. Then we put the pin modulator, that pin modulator then put that 1 kilohertz. The pin modulator is biased, the biasing pin modulator, that the power supply here, this is the modulating voltage. So, we have a 1 kilohertz square wave signal. Please show here, we have a 1 kilohertz square wave signal. So, this is the DC bias this gives. So, this is the on, and when it is not getting, this is 0. So, this is some 5 volt something is given. So, this is the forward bias, this is the reverse bias. So, in the reverse bias the transmission goes on, in forward bias the transmission is cut off.